In the last video, I talked about maximal ideals in a ring. I showed in particular that every commutative ring with unity has a maximal ideal. We used what was called Zorn's lemma for this, and as I told you in that video, this is an important fact, though proof is not that important. So if you are unfamiliar with Zorn's lemma, you don't need to worry about it. It's the statement of the theorem, which is that every ring contains maximal ideals, that we will use in this course. So we also talked in the previous video or the last two videos about prime ideals. Prime ideals and maximal ideals are important classes of ideals in a ring. And we also talked about integral domains. Integral domain is a ring where the zero ideal is a prime ideal. So in this video, I'm going to do some problems to get familiarized with all these concepts that we are doing in the last few videos. So this is a video containing problems. So the first problem is the following. So show that a finite integral domain is a field. So remember that what is a finite integral domain? You know what integral domain is. It's a ring where the zero ideal is a prime ideal. Finite simply means this has only finitely many elements. So let's do this. So let R be an integral domain and suppose that R is finite. So this is the hypothesis. So in other words, R has only finitely many elements. So let's list these elements. So they are, let's say, called A1, A2, AN. So say R is like this. So remember, this is where the finiteness assumption is critically used. R has only finitely many elements, say n of them. So I will call them A1, A2, AN like this. Now I'll consider the following. So of course, remember that 1 is an element of R. I'm not specifying what 1 is. 1 could be A1, 1 could be A2 and so on. I don't need to know what 1 is. I'm just listing all the elements, they're all same to me. Now multiply each element of R, let's say by A1. So what I'm doing is consider A1, A1, which is A1 squared, A1, A2, A1, A3, A1, AN, right? So let's consider these elements. I now claim that these are all distinct. This is my claim. So you choose A1, multiply A1 with every element of the ring. I claim they are distinct. Why is this? So let's prove this. This is because suppose they are not distinct. Maybe when you multiply two different elements AI and AJ, when you multiply with A1, may become equal. That's a possibility. I'm saying that it doesn't happen in an integral domain. So suppose A1 AI is equal to A1 AJ. Suppose this happens. If A1 AI is equal to A1 AJ, I claim that this implies, by usual ring theory, ring properties, this is A1 times A1 minus AJ, right? If I'm taking A1 AJ to the one side, factoring A1 from each term and writing A1 equals A1 AI minus A1 times AI minus AJ is equal to 0. But now, since R is an integral domain, remember R is an integral domain, we know that one of the equivalent properties of an integral domain is that if you have two ring elements whose product is 0, one of them is 0. So A1 is 0 or AI minus AJ is 0. So now suppose A1 is not 0. So I'm going to assume that A1 is not 0. You will see why I will assume that in a minute. So I am assuming A1 is not 0. Remember, I am choosing A1 to begin with. So I will only deal with non-zero elements. So A1 is non-zero. So this is not possible. That means AI minus AJ is 0. But that means AI is equal to AJ. Okay. So in other words, what we are saying is that if A1 multiplies AI and AJ to the same element, in other words, A1 AI is equal to AI AJ, then AI is equal to AJ. So what did we conclude? Hence, if A1 is not 0, then A1 squared, A1 A2, A1 AN are distinct elements. In other words, so R is equal to A1 A squared, A1 A2, A1 AN. Remember, because R is a ring, when you multiply elements of R, you again get elements of R. So the set A1 squared, A1 A2, A1 AN is certainly a subset of R. But because R has n elements and these are n distinct elements, it must equal R. So R is equal to this set. But 1 is contained in R. So 1 is contained in this set A1 squared A2, A1 A2, A1 AN. So A1 AI is equal to 1 for some I from 1 to n. We don't know what it is, we don't need to know what it is, but for some I, A1 AI is equal to 1. So A1 has an inverse, has a multiplicative inverse, I should write. So A1 has a multiplicative inverse. So as soon as A1 is non-zero, we are concluding that A1 has a multiplicative inverse. The same argument works for any non-zero element of R, right? We started with A1, but instead of A1, we can choose any non-zero element of R and multiply by that, argue that there are n distinct elements. So one of them must be 1, so that element has an inverse. Hence, in other words, R is a field. So as soon as you have a ring where every non-zero element has a multiplicative inverse, it is a field by definition, right? A field is a ring where every non-zero element has a multiplicative inverse. So I've assumed that R is a finite integral domain and showed that R is a field. So this is exactly the problem. Now before continuing to the next problem, I'm going to give two examples to illustrate the fact that both statements that we have finite and that it is an integral domain are crucial. Without that, you can't conclude that R is a field. So let's consider R to be Z, the ring of integers. So this is an integral domain. But not a field, right? That we know. It is not a field. Because for example, the integer 2, which is a non-zero integer, has no multiplicative inverse. So it is an integral domain, it's not a field, and the reason that the previous problem does not apply here is R is not finite. So the previous argument won't work here, because for example, if you multiply every element of integers by 2, you get 2n, where n is in Z. This is not equal to Z. When you multiply all elements by 2, you get also an infinite set using the previous problem's argument, but it's not equal to Z. So 1 is not in this. So in other words, 2 does not have a multiplicative inverse. So the previous argument is critically dependent on the fact that R is finite. So if you have an infinite integral domain, it need not be a field. On the other hand, if you have a finite ring but it's not an integral domain, again it need not be a field. So this is not a field. So this is an obvious statement because a field is by definition an integral domain. So this is not an integral domain. And I will quickly tell you why the previous argument fails here. So for example, if you take, remember 2 bar has no multiplicative inverse in this ring. So if you z mod 4z, remember, is the set of residues modulo 4. So their elements can be written as 0 bar, 1 bar, 2 bar, 3 bar. If you multiply each element by 2 bar, what do you get? So you get 2 bar times 0 bar, which is 0 bar, 2 bar times 1 bar, which is 1 bar, 2 bar times 2 bar, which is 0 bar, 2 bar times 3 bar, which is 6 bar, which is 2 bar. Okay, so after multiplying by 2, we have only 2 distinct elements, not 4 distinct elements. Earlier in the case of finite integral domains, when you multiply by a non-zero element, you get all the ring elements. Here you don't get all the ring elements, you get only 0 bar and 1 bar. Sorry, 0 bar and 2 bar. I should write 2 bar times 1 bar is 2 bar. So 1 bar is not one of these products. So 2 bar has no multiplicative inverse. So these examples show that if you have an integral domain but it's not finite, it is not a field. If you have a finite ring that's not an integral domain, also it's not a field. Okay, so let's continue now. So I'll do one more problem now. Next problem, problem number 2 is the following. Let's consider any ring R without any further assumptions. It's R is a ring, and let I and J be ideals of R. Let I and J be ideals of R. So I want to show that any element in I intersection J, okay, so actually I should not write it like this. So I'll write it like the following. Show that the residue, I'll explain this, residue of any element of I intersection J in the quotient ring R mod Ij is nilpotent. Okay, so this requires a bit of an explanation. So let me carefully explain what do I need to do here. So before I do the solution. So remember, if Ij are ideals, implies the product is also an ideal. So this is, in one of the earlier videos I defined the product of two ideals. So these are elements which are obtained by taking products of elements of I and J and adding any finite number of them. Okay, so the way to remember this is Ij consists of finite sums of products of elements of I and J. So this is an ideal, which is an easy verification. So we can consider R mod Ij. So the quotient ring. Remember, every time you have a ring and an ideal in that ring, you can consider the quotient ring. Now the problem is saying that if, so let A be an element of I intersection J, residue of any element of I intersection J. So let A be an element of I intersection J. In other words, A is in both I and J. We want to show that, we have to show that the residue of A in R mod Ij is nilpotent. Residue is denoted by A bar, but remember it is the coset of A. So residue of A is A plus Ij, and this is an element of R mod Ij. Remember, the quotient ring as a set consists of all left cosets under the operation of addition. So residue of A is this. Finally, what is nilpotent? This is something I defined in a previous video. An element of a ring is called nilpotent if a power n is 0 for some positive integer n. Right? A is called nilpotent if some power of a, when you multiply a with itself certain number of times, you get 0. We want to show that a plus ij is a nilpotent element of the quotient ring R mod ij. In other words, that is, we want to show a plus ij power n is equal to 0 for some n. Right? This equality must happen in the ring R mod ij. Right? Because residue of a in R mod ij is nilpotent. So a plus ij power n is equal to 0 for some n. But remember, what is a plus ij plus power n? Under the ring, under the definition of multiplication in the quotient ring, this is simply a power n plus ij. But let me actually write 0 bar here, because 0 means you might be confused with the 0 element of the ring. So 0 bar is the 0 element of the ring R mod ij. So a plus ij power n is an plus ij. Remember this, in order for this to be equal to 0 bar, we want a power n is ij for some n. This is now, after translating everything in the problem, this is what we are reduced to. If a belongs to I intersection j, a power n belongs to ij for some n. Now once you identify that this is what you need to do, it's clear what n you need to take. Remember what is known about a and a? It is in I intersection j. That means it's in I as well as it's in j. Once that happens, a squared, remember, is in ij, because a squared is a times a. A is in I, a is in j. If you recall, the product of two ideals is sums of products, one from the ideal I, the other from the ideal j. Here I am just taking a single product, a times a is in I, a is in j. So a times a is in ij. That means a squared plus ij is 0 in R mod ij. So that means, hence the conclusion is a bar is nilpotent in R mod ij. So the question was, show that any element of I intersection j, the residue of any element of I intersection j is nilpotent in R mod ij. We have shown that, in fact we have shown that a square of any element of I intersection j is 0 in R mod ij. It's not just nilpotent, but the power you need to take is just 2. So the next problem I want to do is building on this notion of ij and the quotient ring R mod ij. Okay, so let me now do the following. Let R be an arbitrary ring. This is as before. In the previous problem also we started with a ring. And let I and j be two ideals. Let I and j be two ideals of R. So I have a ring and two ideals of R. Now I am assuming something about these two ideals. Assume that I plus j is R. And again, just like the product of two ideals, we have also learned about the sum of two ideals. And what is the sum? So recall. So I'll use the color red for recalling. I plus j, unlike the product, I plus j is simpler actually. All you need to do is a plus b, where a is in I and b is in j. So you can take two elements, one from I, one plus j, and you take their sum. If you take this and you take the collection of those elements, it's actually an ideal. That's an exercise from a previous video, and it is what we call the ideal I plus j. So I plus j is this. Okay. So now I'm telling you that that is equal to R. That's not in general true, but in this problem I am assuming that I and j have this property that I plus j is equal to R. I need to now prove the following statement. So there are two parts to this problem. We'll first state 1 and solve it, and then we'll state 2 and then solve 2. Show that the first problem is Ij is equal to I intersection j. Okay, so the solution of this I will do first. So under the assumption that I plus j is equal to R, show that the product is equal to the intersection. So there is one obvious inclusion. So in order to show equality, we will show that Ij is contained in I intersection j, and we also show that I intersection j is contained in Ij. Note that the inclusion Ij is contained in I intersection j always holds, and this is an easy check. What I mean always holds is we don't need the hypothesis that I plus j is equal to R, right? So this is in general true, not just for ideals whose sum is R. Why is this? I will show you quickly why is this. So why is this? Take an element of Ij. What is an element of Ij? Arbitrary element is of this form, right? Ai is in I, Bi is in J. So take an arbitrary element. Now Ai is in I, so and Bi is in J. That means Bi is a ring element, Ai is a ideal element. That means Ai Bi is in I. Because remember, an ideal has the property that anything in the ring times anything in the ideal is in the ideal. So Ai is in I, Bi is in the ring, that means Ai Bi is in I. But similarly, for the same reason, Bi is in J, Ai is in I, that means Ai is a ring element, Bi is the ideal element, the product is in J. That means Ai Bi is in I intersection J. Once Ai Bi is in I intersection J, this whole thing is in I intersection J. Because I intersection J is an ideal, this is something we proved earlier, or I have asked you to prove. So if you have a bunch of elements inside I intersection J, their sum is in I intersection J. So all these elements are in I intersection J, so their sum is in I intersection J. So the inclusion Ij contained in I intersection J is trivial, it's very easy. Okay, so now we'll prove that the opposite inclusion holds. Now we will show I intersection J is contained in Ij, and this is the crucial inclusion that's not in general true. After solving this, I will give you an example. This requires the hypothesis that I plus j is equal to R. So now, since I plus j is equal to R, the element 1 belongs to I plus j, right? Because the identity element 1 is a ring element, it's in R. But I plus j is equal to R, so 1 is in I plus j. So there exists elements R in I and S in J such that 1 is equal to R plus S, right? So 1 is an element of I plus j, and I recalled for you what is I plus j. I plus j is simply the collection of sums, one from I, one from j. So 1 is equal to R plus S. Okay. So now I am trying to show that I intersection j is contained in Ij. So let us choose an element A in I intersection j. We will eventually show that A is in Ij. Okay. So now 1 is equal to R plus S, that we know. So we can write A is equal to AR plus AS, right? I am multiplying both sides by A. 1 is equal to R plus S means A times A is equal to A times R plus A times S. This I claim will give me what I want, because let's look at AR. What is R is in I. A is an arbitrary ring element. So AR is in I. Fine. A is an arbitrary ring element. R is an element of I. So this is in I. Similarly, S is in J. A is an arbitrary ring element. So AS is in J. So AR is in I, AS in J. So that means this is an I plus J. Right? So we have written A as something in I plus something in J. That means, and that's all. We have started with an arbitrary element of I intersection J, and we have concluded that it's in I plus J. Hence, I intersection J is I plus J. So we have the other inclusion always holds. So I plus J is equal to I intersection J. So, and in the second inclusion, we needed crucially the fact that I plus J is R. So now, in general, as I told you earlier, this is not true. So let's take R to be Z and I to be 2Z and J to be 4Z. So the ideal I is all even integers, the ideal J is all multiples of 4. What is IJ? In this case, you can check that it is simply 8Z. So you take products of I, elements of I with elements of J, and you add them. Everything happens to be a multiple of 8 because 2 times 4, that is a crucial idea. And what is I plus J? If you think about this, actually I made a mistake. So I am not interested in showing that, I have to go back here. I am not interested in showing that I intersection J is contained in I plus J. I plus J is R. So of course I intersection J is contained in I plus J. What I want is A is contained in IJ. So now, so what I want is A is contained in I intersection J. So let me go back here. A is contained in I and and S is contained in J. So AS is contained in IJ. So this is something I missed here. Similarly, A is contained in J and R is contained in I. So this implies AR is contained in IJ. Okay, so I should have written here A is, remember I have never used that A is actually in both I intersection J, both I and J, that is crucial here. So A is contained in I, A is contained in J, whereas R is contained in I, so AR is contained in IJ. It is a product of something in I, something in J. Similarly, AS is also a product of something in I, something in J. So AS is contained in IJ. So A is equal to AR plus AS. It is something in IJ plus something in IJ. That means A is in IJ. So what we have shown is that I intersection J is contained in IJ, and hence I intersection J is equal to IJ. Here I showed that I intersection J is already contained in IJ. Here we showed that IJ is contained in I intersection IJ. IJ is contained in I intersection J. This we have showed. Now we are trying to show that I intersection J is contained in IJ. So I intersection J is equal to IJ. And now this example shows that I intersection J is in general not equal to IJ. So IJ in this example, when I is 2Z and J is 4Z, IJ is 8Z. This is easy to check. And what is I intersection J? Remember, in this case, J is actually contained in I because every multiple of 4 is definitely even. So if you take intersection of I and J, you will get J. So, and of course J is 4Z. So the intersection of the two ideals is 4Z. The product of two ideals is 8Z. So IJ is not equal to I intersection J. But one inclusion always holds. IJ which is 8z, is contained in I intersection j. In the solution, if you see, what always holds is that the product is in the intersection. That we have. What we don't have here is I intersection j is contained in ij. So this does not happen, but this inclusion always holds. And the problem here is, why does the argument in the problem does not work? Why does it not work? It's because the sum of these two ideals, and this is an exercise for you, I will leave it for you to check. The sum of these ideals is actually 2z, and it is not z. If you take the sum of elements of I and j, you get actually 2z, which is not equal to the full ring. So the sum is only a proper ideal, and hence the argument in the problem does not work, and we do not have the equality of the product and intersection. So just remember that product is always contained in the intersection, but for intersection to be contained in the product, you need to assume that the sum of the ideals is the full ring. So sorry about the confusion in this problem, but I hope it's clear now. So I'll stop this video here. In the next video, we'll continue solving more problems. Thank you.